We're going to be, is it audio? Anyone monitoring the audio?
We'll check it.
Okay, great. Thanks. So this morning, I want to thank everyone for making it all this distance in, despite such, okay, sounds like it's working, despite such adversity in the weather. Today, we're going to be really diving into a couple of lectures of coverage of one of the most important topics in the book Functional Programming in Scala, in functional programming in general, and specifically for its implications for data science. This is a topic that lies at the heart of the scalability and flexibility and power of the Spark platform, which we'll be using in earnest through most of the course, starting in a few lectures. And it's also a technique that makes functional programming languages exceptionally suited for adaptation in a metalinguistic sense, in the sense of adapting essentially their syntax to support new domain-specific languages. These are techniques that have for decades been explored in the functional language context, the use of little languages, purpose-built languages supporting certain domains of activity. And Scala, as one example in that space, provides particular degrees of support because of its transparent its transparent way in which it offers three types of laziness that we'll be talking about, or three types of non-strictness. And in this lecture, we're going to be introducing those three and three major exemplars of each, namely use of lazy values, use of call by name, and in the form of streams. Okay, and we will further be examining the difference of these from each other and talking about the two major ways in which non-strictness is supported in Scala and by extension in Spark via a mechanism called call by need and another one called call by name. And we'll contrast the use of methods that involve recomputation of values when needed as compared to values where memoization is used, where once a value is computed, it's saved away in a way that allows us to sort of reuse it without recomputing it. And we're going to be going through some material which covers each of those major types of non-strictness and applies them with a particular emphasis on streams, okay, and use of streams in pipelines. Now, in order to get into this, I had asked you to undertake an exercise for this instance of the class, which involved the use of a pipeline to read a textual file, which is then processed in successive stages to extract certain types of information from it, such as the counts of things of different sizes, of words of different sizes in it, or the count of instances of particular words within that document, etc. And this pipeline is one which could be applied in a context of non-strictness, of laziness in the form of streams. And it could also be applied with traditional data structures, such as vectors, arrays, or other sorts of strict collections. Before diving into sort of non-strictness in general, I'd actually like to, as I am wont, I'd like to cover this little example. Okay. So you will recall that I gave a request that for you to try processing a document, and there was some futzing with the URL here. I think it was Yuan who pointed out some issues with going through Google Docs or Google Drive to read it, and so I ended up posting just on an HTTP site to my faculty site. And what I requested here was that you use pipelines to count a couple of quantities: number of recurrences of certain words, number of recurrences of words of a certain length. So words of length 2, words of length 3, words of length 1, words of length 10, etc. And then each of those sorted by the occurrence count. And I suggested starting with this sort of mechanism, which did involve a stream, which was a construct we'll be looking at today. For transparency, I'll be also showing how it can be done with an array. And I noted that, that in processing this, we're going to need several constructs that we've used before, say in our examination of error handling, and before, in fact. So map, filter, and this thing called Flatmap. Okay, Flatmap will be particularly important here in allowing us to map from lines on the one hand to lines that are obtained here to map to particular words from within a line. Okay, and I gave a reminder on that and on group by, which produces a map that maps from some keys, and say a word, to a value associated with the key, say the number of counts of that word. Okay, or maybe it maps from keys that represent the length of a word to the number of counts of that length, right? It turns out that this whole use of key value data structures is very prominent within Spark, okay? And in fact, when Spark streaming, which we're going to be examining in this very room not 2 months hence. So the use of key values here is more than just kind of a step towards an end. It's I would like you to pay attention to it, because it will form an important part of our pursuit of other data collection tasks within Spark. Okay, so I'd asked you to undertake this, and I had given some code up front, which by which you can get a stream of words. Okay, and I'd like to follow this through, and I'd like to make sure we understand each step of it. Okay, and to do that, I am going to go to the Spark shell here. Oh my gosh. Okay, somehow I forgot arguably the most important part of being in this room, to wit, the use of the screen, and I'm relying entirely on the online mechanisms. So pardon me while I just look to see if I can engage said screen. But alas, I fear my adapter was judged faulty, and I actually am bereft of an adapter here to HDMI, between HDMI and VGA. Can people see me online? Okay, we'll have to make do with that. Can you see my screen? Okay, we'll have to make do with this, as does the vast majority of the world. Apologies, I still have to go get another adapter, and mine is apparently trapped in my office right now. Merlin was going to go get one, but I'm not sure he has. Okay, so I'm going to invoke the Scala shell. Now, this can also be pursued from Zeppelin, and I would do that, but I want to get started shortly, and I'm just going to do it here if that's okay. So we have to paste this in carefully. So I am going to go and copy the basic elements that I've given you over into this. I have to be careful because they're split among a couple lines. So what we're doing here is, and actually I need to import, before doing this, Scala.io, I think. It'll be an unhappy camper. Import Scala.io, and we want to import all of the stuff in it. Okay, here we go. So this first element is going to open up this document. This is characterizing the encoding used in that document, and this is getting the lines from that document. You'll notice that gives us what's called an iterator. Okay, it gives us the capacity to iterate over the lines, to successively obtain the lines. But generally, we're not interested for our purposes in these large arrays and working in these large pipelines and working with an iterator. We actually want to turn it into a collection of some sort. Okay, and what I had suggested was turning it into a stream. Because streams give you the experience of working with these lazy constructs. I'm going to do that here. Now, at certain times during this presentation, I may also use another component, which is to array, for example, or to another type of collection. And you notice if I do that, it starts to give me, oh my gosh, what's moved permanently? Oh, that looks particularly boring.
I had to use HTTPS.
Oh.
www.cs.useas.ca.
Oh, wow. Okay. Okay. Well, I stand corrected. There we go. Okay. Move permanently. This document has been, to HTTPS. Okay. Okay, well, learn something every day. Okay, there we go. Okay, there we go. Now we're talking, right? Okay, so let me copy this down because I may employ it later. Here we go. Okay, there we go. Okay.
When I used this, the link that you...
Yeah, that's fine.
I got the HTML, like the syntax of the HTML.
Okay.
Yeah.
Yeah. I mean,
I thought this is what
that's fine. We're going to have different content presented here. But
I used from file instead.
Oh, you did from file. Okay. Yeah, that's great. That's great. So it was my intention to go to this document, but that's fine. Okay, so ladies and gentlemen, here's ToStream, and this gives us the same contents, but it gives it to us in a potential form, right? One of the key ideas behind streams, which you should have learned from chapter 5 of the book, is a separation of, on the one hand, description of computation from number 2, when you have to execute it. So streams allow us to name a computation, which is potentially of arbitrary length. Like it could be as long as needed. It could in principle be unbounded in length. And they separate that naming of it, the ability to sort of characterize it on the one hand with, in the ability to characterize it and kind of package it up in a way that it can then be incrementally exercised, be incrementally sort of computed, to separate that from when we do that incremental computation. This is very important. A stream remembers how to compute itself. You know, you have a stream and it knows how to get the next element. It knows how to do the successive computation. And just like a closure remembers how to do its job. When we call it, it knows all the information to do its job. A stream knows all the information it needs to get its successive elements, right? And it's abstraction that, as a stream, hides all of that from us. We don't have to worry about what the computation is by which it was created. It could have been with this computation or that one, any of hundreds or thousands or millions of computations. But the point is, it knows how to give us the next elements, right? Okay, so we're going to explore this stream here to successively process it. And you notice whether we turn it into a stream or an array, it gives us back a collection. The stream is has the potential for computing the rest of it. The array actually sucks the elements in and sucks them all into it at once, all the lines in this case. Okay, so what I'm going to do is ask you to now, having done that, and I'd ask you to get it with HTTPS, with the www side. I'd like you to go and follow the successive components of the computation that I laid out here. So I'd like you to perform a flat map on this, okay? And we're going to see how that affects the results here. I asked you to do it to a stream here. And so we'll undertake that. Here we go. And you'll notice that what comes back is a stream of what? What is this? This is a stream of, what does that look like?
Words.
Yeah, it's of words, right? And if I did take 20 and I did force here, what I will see is, in fact, successive words from it. These are the first 20, right? I told it, give me the first 20. And I forced them to be shown, the design and use of, right? And so what happened here is that that the lines got rendered into words, the design and use of a smartphone data. And then the next line was collection tool and accompanying configuration. And now they've been rendered into words. Now, how did that happen? What allowed that to happen, that we went from lines, as shown up here, to those specific words? Can anyone characterize it? What happened? Why did adding this little thing here allow us to do that? What's conceptually going on? What does this split do?
Split the characters until, like, finds something different than the characters, like this case.
Okay. Yeah. So in this case, we are splitting based on a character which is anything other than in the alphanumerics, A through Z, instead of the standard English character set, right? And so that's splitting up these original lines into particular words according to those boundaries, right? Now, why flat map? Let's suppose we had done map instead of flat map. How would the results have been different? What would a map give us?
Gives you a stream of words, so each word in a string.
Okay, so it's giving each word, but you'll notice how it's giving each word here. What's going on here? Can anyone see? Does anyone remember in our past session when we were working with option or working with try, seeing something a little bit similar? What's going on here?
Each line has an array.
Yeah, each line has an array. So it was kind of like last time we had an option which included within it an option. Do you remember that? It was kind of nested. We got back an answer. Instead of being sum of 3, it was like sum of 3, which wasn't what we wanted. We wanted sum of 3, but it gave us a nested construct. And why is it? Why is it that Like, why is it that this is an array and this is another array? Whence do those arrays come? Where did those come from?
8 lines, because we have lines.
Yeah, each of these came from a line. So if we just mapped each line, remember what map does, right? What's map's job in life? Well, it takes in a function and a collection, right? It's applying this function to each successive element of the collection. And it creates a new collection of what size? Well, the same size as the collection to which it's applied. So each element in the original collection is mapped using that function. Function is applied to it, we get out a single element, right? So the collection to which we applied this split was, we applied the map, was a stream of what? Of, begins with L. Lines. Yeah, thanks. When we applied map to it, we got out a stream of equal size, where each element of the stream we got out was the result of applying the function to the corresponding element of the input collection. So here, each element that we got out was the result of applying a split, right? Okay. So just to be clear here, let's examine this split operation, okay? Because I want to be clear how split operates. So let's give it a turtle, a name here, okay? So I'm going to say here, foo bar, right? And I'm going to say split. Now I'm going to use the same regular expression. So I'm also introducing, just sort of in passing here, what are called raw strings in Scala. Scala supports several types of strings, okay? And one of the types of strings it provides is kind of a traditional string, which will do some interpretation of the string. So \n will turn into new line. \r return to carriage return. \t will start into tab. A second type of string it supports is a raw string. There's no interpretation done, okay? So if you have a character like \, it uses it as a backslash. So if you \n, it's actually \n. A third type of string that it supports is something called a substitution string, which allows you to substitute in the value of a variable or value, or a computation, an expression. You could substitute that. And we actually saw that in a previous lesson where we had S and then the name of the string. So this would give a substitution string. This would give a raw string. Alternatively, you can use, if I recall correctly, 3 double quotes. Start it. You could do like this sort of thing. And that will also serve as a raw string, if memory serves me. Okay, so here we interpret it. Just so you're clear about the whole string stuff, if we had, if we did this, print raw, foo /bar, then it's going to do that, right? But if I did print of this, what am I going to get? What am I going to see differently? I'll get that. Do you see the difference? This is raw string. This is non-raw string, cook string. And then just for completeness here, I'll show you val my var equals zap. Okay. Okay, and then I could do print substitution string. Well, watch this. I won't do a substitute. I'll do a regular string. My var I'll do my var, and this is just a regular string, so it's going to print that out. If I do this, what am I going to get? I'll get out the value of that. Do you see that? It just substitutes it out. If I have a dollar sign, see that? This is a substitution string. See that? These are three types of strings there. And actually, I could do more complex things like this. This is concatenation in this case. I need a quote, but anyway, I'm not going to do it. Okay, fine. Okay, so ladies and gentlemen, back to our task at hand. Here we are splitting by this thing, and it splits it into an array. Do you see that? And if we did, you notice it's not just space. So if we did, for example, lickety split, it'll split it into two things. Why? Why is this splitting it into two? Because dash is not an element of this. Dash is not an alphanumeric, right? Okay. Same thing with, if I had done that or something like that. Okay. So in short, this split is dividing up each line into an array. Do you see that? It's taking the string and turning it into array, right? Takes the string, turn it into array. This takes each element, this map, for each element of the stream, which is a string, it splits it into pieces, which produces an array, right? And that's why we get this stream of arrays. The first element of this stream just comes from applying this function, to wit, the split function, to the first element of the stream. In other words, the first line. The second element here comes from applying the split to the second element of the stream, namely the second line. Yeah? Is that clear? Okay. So the job in life of this split is to turn strings into arrays, and therefore we go from a stream of strings to a stream of exactly the same size but containing arrays. But we don't want that generally. Here we certainly don't. So we have to use not map, but what? Flatmap. Flatmap. So we're gonna get it as a bunch of words. Okay. Now, Flatmap is so much more than a way of than a kludge to kind of get it into a sort of flat form. Turns out it's much more deep than that. It has to do with sequencing of operations. It's a way in which we impose sequences of operations using monads, but that lies in the future. Okay. Okay. So anyway, we did that. Okay. So that gets us a stream of words. Now, how are we going to pursue our query? How are we going to go from that stream of words, which I gave you the recipe for, or which I gave you the recipe? How are we going to convert that into getting these things here? Anyone?
Filter first.
Okay. Okay. So.
Damage lines.
Okay. So what would you like to filter by?
Is empty. What is empty?
Okay. Okay. So thank you, Will. So we have a lot of these lines which are empty lines, right? And if we go and we look here at the first bunch of elements, we'll find that we have, and let me do it with Flatmap here, so we could see it in the collection here. We have a number of these sort of empty strings, right? Which came from empty lines. So let's filter those out. Okay. So how are we going to filter them out? Anyone? Yeah. So we use filter, and what are we going to filter? Yeah, sure. We could use,
in-
oops, we could use this thing not equal to empty. Now, we could also test, and this could be more robust in some contexts, to test if the length is 0, right? Because it might not be obvious to us for non-printing string. So I'm going to actually do that, here, so that we filter them out in a little bit of a more robust way. Okay, because sometimes we could have non-printing strings, etc. Okay, now how are we going to continue then? If we want to try to count the number of occurrences of words, what do we need to do here?
Group by.
Sorry?
Group by.
Okay, so what do we group by? So group by gives us a map. It gives us a map which states for each key some value for that key. So this sounds tempting, right? We want to keep track for each thing. We want to keep track of some quantity, some number, right? What are the things for which we want to keep track of something
Group by
here?
identity.
Okay. So we're counting here words. So we want to group by identity. Okay, good. So let's go and we will say dot group by. And here we want to group by word. So we want, if that word occurs, in several instances for each we want to count, right? So we want to do group by word, okay? So we're going to group by identity, or let's say string goes to string, right? Okay. And then what is that going to give us? Group by takes in, it's applied to a collection. We give it a function that tells us for each element of that collection what the key is. And what does it give us back? It gives us back, begins with an M, ends with a P. It is an A in the middle, and it's not Pam. What is it? Map. Yeah, it gives us back a map with a capital M. Okay. Here it is. There it is. It's an immutable map. Now notice I said the function specifies for each item in the collection what the key is, right?
Mhm.
What the key is. But what I didn't specify is what it does for the values. What does it do for the values? What does it do for the values here, ladies and gentlemen?
Number of occurrences.
Okay, well, this is so it's a good question, but it's actually much more flexible than that. We can use it to do that with a modicum, a small bit of additional processing. But in fact, what it gives us is for each of the keys, it gives us a what? A collection. It's a collection. Which collection is it? Well, it's the same sort of collection we applied it to. So here we applied it to a stream. And so for each of the keys, it gives us a stream. Do you see that?
Yeah.
Now, the intriguing thing that this shows us is you'll notice it gives us a stream. What's going on here? Why do we see question marks still? Well, it hasn't fully evaluated just what elements there are in there, right? It knows there's the pathogens, but it hasn't found all the occurrence necessarily of it to do this. So I'm going to actually show you what the corresponding thing looks like with array here. Here we go, array. Boom. So with an array, here it's, what is this? This is an array of each what? Or rate. I don't know what G is. Jubatier or something. So what are these things here?
stream of these words.
Okay, yeah, or the collection of these words. What do each of them represent? Like, how is this rate different from that one?
They're all individual occurrences of it.
They're individual occurrences that occurred somewhere in the document, right? Okay. Okay, so that's interesting. Look at this is a student of mine. You can tell. Look at the abstraction things. Good man, that Dylan. Look at that. You know, I was once told in grad school, I was told, when you're going to give a talk, you tell them what you're going to tell them, and then you tell them, and then you tell them what you told them. and that's what he did with abstraction, I guess. So ladies and gentlemen, each of these represents a specific occurrence within the collection to which the map is applied. And it's grouping, in short, all things which share the same what? Key. All things which share the same key are grouped together, right? Okay. To illustrate this point, at the cost of kind of a linear presentation, I'm going to ask you, suppose we wanted to pursue, how would this differ from number of occurrences of word lengths? So we've here grouped by keys which represent the word itself. Suppose we want to instead count the number of occurrences of a given word length. What would we instead group by? Group by length. So how would I change this? Well, string length. Yeah. Okay. Okay, now check out what we got. Ladies and gentlemen, what is this 5? Whence does it come?
The words that has 5.
Yeah, length 5. And you notice that these are all the elements of the original collection to which I applied the group by, which all of these share what characteristic?
5 letters.
They consist of length 5. You see that? And similarly, there'd be a collection of length 1 and 2, etc. Right? We could go see that. Okay, so ladies and gentlemen, the map that's output by the group by groups for a given key. In this case, the key is length. It has a collection of all the items that have that key. In this case, it's all the words of that length. If I simply group by the word itself, then the collection is not terribly interesting, but it's all the instances of where that word occurred. Do you see that? Mm-hmm. Great. Okay. So, ladies and gentlemen, so now we want to go and count the number of occurrences of words. How do we do that? Okay, map values. And what do we want to map each value? So the value is going to be what here? Yeah, this is going to be the collection. So we're going to map it to length, right? Mm-hmm. And you notice I'm doing something subversive. I'm undertaking something insidious. There was a time where functional programming was almost subversive and insidious, and I practiced it in secret. You can go read about the Knights of the Lambda Calculus, a secret society for functional programming. But actually, now functional programming is all the rage. But what I'm actually introducing here that's a little bit insidious is or a little bit subversive is, you notice I've selected what? Parentheses, ladies and gentlemen. Notice I'm not calling like this dot length like that. By Scala conventions, if it doesn't take any arguments, you drop the parentheses. If it takes 1, you might well drop the parentheses. Okay. but here we're mapping to lengths. Okay, so what are these lengths? What does it mean by clauses has 13? Abstraction has 24. What does that indicate?
The number of occurrences.
Number of occurrences. That's right. That's right. Excellent. Okay. Okay. And now, how would that differ from if I had wanted to count the number of occurrences of a given word length? What would I change here? Yeah, dot length here, right?
Yeah.
There we go. And here, 5-letter words, there are 3,967. Okay. 10-letter, 1941. 2-letter, 6,093. Right. Okay. And 4-letter, all of them proper, I assure you, 5,883. Okay. So, ladies and gentlemen, we have here a count of different lengths, right? Yeah, there's one 36 length word. Yeah, it's a long word. Yeah, yeah, I'm not sure what word, but you could go and find out, right? You could go and look up what was that word, right? So, well, here let's do that. A 36 length word. How would we do that? There's a 45. Okay. Okay. How would I do that? Okay. I don't know that there's a filter values. It could be. Scala has all sorts of neat things, but I don't think that's one of them. But what can we do to extract things that are of length 45? What would we not do here? What would be different? What would we not want to do? If we want to find which word it is, what would we do? Okay, that's a great idea. That's a great idea. I was thinking of going and getting the map and looking up that key, but filtering by length is a good one. Okay, so let's go. But there's something more we're going to need to do to make it a meaningful thing. So let's filter all lengths greater than what, 30?
Yeah.
Okay. But why isn't this going to give me what I want?
Yeah, this one.
So if I do this, it's going to tell me the count, but it's not going to tell me what they are. What do I need to do to show it which they are? Yeah. Well, okay, yes, I could do that. That's an interesting thing. So I could go and I could do this. Okay. Right. These are. It's unclear how they fit in there. I thought they might be Osgood variable names, but they're they're not. Are they LaTeX things? I'm not sure. Anyway, labels. In any case, they're not. It's not clear that they're all English words. That's for sure.
No, it is English word, but I mean, there's no space.
Yeah, but I mean, it's actually, that's not a English word. Like, there are English words which are very long, I suppose. Super fragilistic. What is it? Yeah.
I think it's at the name of.
I mean, this is a name of variables because I mean, it's meaningful. Like it helps pathway, experiments, employee, employing.
Yeah.
API. So like it's
yeah, it's some of them could be variables, but I think some of them serve other uses. And if you want, you could read the thesis and try to find out. Maybe that will tempt you. Okay, ladies and gentlemen, let's go and we will now pursue. So that was for looking at. We could look at here these that had different lengths, and we could see which they were, for example, right? Suppose we wanted to sort by now things that have large lengths. So we're going to go back and look at all of those. Now, suppose we want to sort by things of a certain length. So we want to, how did I phrase it? Sorting by the count of occurrences. How do we do this? Well, I pretty much give the methods here, right? So this, what's that? Yeah, so we could convert it to a sequence. You notice the sequence gives us a sequence of, what are these things? What is that? Yeah, it's a tuple, right? In Scala, I could create tuples like this. This is a tuple. And these turn out to be really useful, not least for things like multiple return values from a function, for example, right? But one of the ways in which they're useful is you can map into this, right? And then we can sort by what? What are we going to sort by? If we want to sort by the count of occurrences, what are we going to sort by? Probably specify it there. What do we sort by? We'll do sort with, and then what? What do we sort with? Sorry? Yeah, we're going to sort by this value, yeah, which is the second element. So here we can pull in a pair, and that pair is such. And then we can sort by the second value of that, okay? This is a fairly easy thing to do. So this will be a word and count, or count occurrences, occurrences, and we will map it into, oh, I'm sorry. Oh, I stand corrected. There are ways to do things like that in Scala, which are kind of sweet, but with a case construct. But no, here they're actually pairs, right? So pair 1 and pair 2. What are these pairs? Well, we're sorting by pairs, complete pairs, and we have to tell what to sort by. Element of pair 1 is greater than the second element of pair 2, right? Okay, so what did I, okay, not illegal. Okay, so what am I missing there? I would have thought that, oh, of course. Here we are. Okay, so what are these? What's shown before me? So I had, before providing that sort with, I had these things. Well, by providing the sort with, what have I done? This sort with, this function, if you give it any 2 items here, what is it going to do? It's going to compare them in terms of what?
The number of occurrences?
Yeah, the number of occurrences. So the one, what it's returning is whether the first has a number of occurrences that exceeds the second. And it's going to sort based on that. It's going to, the one earlier on is going to be one with a larger number of occurrences. And so this is listing the different count of occurrences of different tasks. Okay, or different words rather. And interestingly, incidentally, this thing is still in there. I guess I neglected to continue on that filter out this thing here. There's no, I had dropped the filter somehow in my code. But this is a decreasing order, right, of the occurrences of those words, right? Do you see that? How about if we want to sort by the count of words of different lengths to see which are the most common lengths? What do we have to change?
The same thing as we have done before.
Okay, so what do we change here?
Dot length
Where do we put it?
and group by.
Group by, exactly. Exactly. Okay, here we go. So which is the most common length of word in this particular document?
8.
3. Followed in short order by 2, followed by 4, 5, etc. All right. And you'll notice 1 does occur, but it's actually, yeah, it's actually far less common. I would hazard that many of those ones are what? A or I. Yeah. Yeah. So this gives us this sense. Now, what we've done here is we've strung together logic that successively processes a collection where each operation on it performs some fairly well-defined task. And part of the power of this that I've tried to emphasize by asking you to pursue these different things, different variants on this, is that these are fairly modular characterizations of our needs. So, for example, if we here want to, sort by to find the most common lengths, we can do that. If we want to find the most common words, all it takes is modification to a single thing here, right? Just a single surgical component, and we find the most common words. Similarly, we could find, the most common letters with a small variant of that, or words that we could classify words, find the most common starting letter of a word, right? By how would we find the most common starting letter of a word? List out the most common starting letters of words. How do we do that? Starting letter, so the first letter of that word. What would we do? Well, one thing we want to be careful is to filter out that. But how would it be different?
By screens.
Yes.
Screens first.
First element. That's right. And so I'd have to go. Remember with strings in Scala, but it's probably like is it left or there's some way to sort of get the first character. Maybe that you can even do something like that. There we go. So what would we do? We'd group by that thing and its first element, but we would need to be careful here that the length is greater than 0, right? Which I had somehow, forgotten. Okay, what is it? Oh, okay, yes. Length is greater than 0. Not that thing is greater than 0. Okay, there we are. Okay, so there's the most common starting word, starting letters. T more than A, more than I, more than S. Okay. If we wanted to do it, notice that we have different capitalizations. How if we wanted to do it without regard to capitalization? What would we do?
I think you need to map each word to lowercase or.
Yeah, we could do that. Okay, so all I do is write str dot, and I think there's a 2 lower, or oops, sorry, 2 lower. and I think it's going to have problems parsing this, but mumble here. Value is two lower is not a member of string. Okay. To lower case. Okay. Okay. I admire their care. It's a lowercase. Okay. Okay. Type mismatch. Okay. I want the 0th element of that. Okay, it's, oh, I see. Okay. Dot. I just want the first element of it. And the problem is that I think to lowercase takes an extra.
Lowercase is for string.
It's for this string. Yeah.
To lowercase is for string, right?
Right. No, but it returns a string, and I'm trying to extract its 0, its first element.
You put string parentheses 0 dot to lower.
Good call. That's easier. That's easier. Good. That's right. I like this guy. Right.
I'm delayed, so.
I think two lowercase is okay. It actually gives back a char. Dot to string. There we are. Okay. There we are. Yeah. Okay. That works. Okay. So the least common letter is Z. Right. The most common is T, and then A, and then S. Okay. Okay. So the point here is that these pipelines are quite modular. We can pursue a different need by simply modifying locally certain components of it. If we want to modify, whether we are listing them all or counting them, we would modify one piece of this, map values. If we want to modify what we are counting, we would modify this piece here with group by. If we want to modify what we want to sort with, we'd modify the sort with components of it. If we want to change whether we're dealing with lines or words, we would change this component here. If we want to change the filtering, we change this component. In short, these are fairly orthogonal. They're fairly modular. More than that, you'll notice that this pipeline is not composed of calls to functions that we have written very explicitly and named and built in our program. What we're calling here, this is not a point to be missed. What we're calling here is actually general higher order constructs. By higher order constructs, I mean here, they are higher order functions. They're functions to which we pass what in this case? In so many cases, what are we doing here? These are functions we're calling, like filter, map values, group by, sort with. And how are we using them? Well, we're passing in functions. We're not writing our own custom function from scratch, which says, what we want to do. We're needing to call that successively. Instead, we're making use of these very general purpose constructs. Mapping, flat map's another example. Map would be another example. Map, filter, reduce, sort with, map values. We're using at a fundamental level these very powerful constructs, which each have purposes in life, and we're tailoring them with closures, with these anonymous functions we're passing. And it allows for a crisp specification of what we want to do that's at the same time very versatile. That if we want to change it a little bit, what we want to do, we just have to modify it a little bit. We don't have to modify it in a big way. We just have to surgically change small things. And there's something very appealing about that when you want to make what's conceptually a small change, I find it aesthetically distressing that if I have to modify a big set of things in my program. Instead, the changes here mirror, by and large, the types of changes that at the level of the concepts. Small things turn into small need changes, change into small code changes by and large. And you'll notice that we elaborated this by extending it, right? We had here a map, for example, and then we said, well, now we want to have it sorted. And so we could go and sort it by adding on a small extra construct. So these pipelines are powerful. They're not just powerful for toy examples, though. They're powerful for composition of needs, such as we'll be having within Spark. And in fact, Spark and Spark ML in particular for machine learning places a very strong emphasis on the use of pipelines and being able to name pipelines, and critically, being able to compose pipelines. Take one pipeline, take another, and put them together so the second operates on the output of the first, okay? And this is quite central to kind of the practice of data science, this ability to name abstractions and combine them flexibly. Here, we are doing it with a simple example, but one that points to sort of the flexibility of this strategy. So you should try to sort of take away from this not just minutiae about processing strings in Scala, but the fact that pipelines are useful, pipelines are powerful, pipelines are especially powerful because they make use of higher order constructs, and pipelines allow for this sort of orthogonal description of our needs, which often adapts in easy ways to slight variations in those needs. Finally, I'll note again something we emphasized last time, namely that the use of pipelines like this make it imperative that if an error occurs somewhere along that pipeline, that we be able to handle it without breaking out of the pipeline. You can imagine, suppose an error were to occur in this get lines component here, or suppose an error were to occur in this filter component or this split component. Handling it in a surrounding exception is a non-starter, because how do we get back into the pipeline and continue processing after we fix the issue? It's not so neatly done to kind of handle it outside of the pipeline. And this is one of the key reasons in functional programming, and in Scala in particular, certainly, we make use of values to, in error handling, like those monadic values, try, option, either, etc., okay, that we saw last time. Those allow for the pipeline to operate on these values that encode errors and just continue processing, short-circuiting the computation where needed to avoid doing needless work if you know you have no values or what have you. And we saw examples of this last time, right? Where cases where you not only have logical errors, but where, by the happenstance, there happened to be no value which matched a certain criteria. And so, that value happens to be empty, and you don't want that to lead to an error. Okay, so ladies and gentlemen, pipelines are good. But there's one final need about pipelines that I've been brushing under the rug. You may have noticed that in a sleight of hand, I deliberately substituted in at some point to array here. I actually did that consciously because I wanted you to be able to see with clarity what's going on here. And specifically, I wanted you to be able to see for each successive operation here what the result is. And going back and unwrapping it, this might be the results here. Before that, we have this sort of thing. Before that, we have what's the output from the previous stage is this. What's output from the previous stage is this. what's output from the previous stage is this. You could kind of trace back the logic, right? All the way, step by step by step. But there's a distressing component of this from a data science perspective when I'm pursuing it with arrays. The distressing component is that each of these steps that I was unfolding there, each of those steps that I'm kind of showing the output for it, as I compose this pipeline, each of those steps involves a really big data structure, right? So that very first step, or one of the first steps here, here where I, go and I get the lines and I do 2 array. This is a big data structure. Here it's big. For data science in general, it's huge. It's huge. And if we then do a flat map, we get out another data structure that's huge. Or it could be huge. And after that, we get out another data structure that could be huge. And it's pretty much a non-starter in a context where memory is really limited to want to kind of go and create all at once these data structures and bring them into memory. So maybe in principle, you think, well, it's kind of a nice idea to process these pipelines, but we don't have the luxury of, operating on these giant data structures each time we map the entire data structure over, because we can't keep it all in memory at once. If this were 1 billion items in the thesis, well, Dylan would still be working on it, but if we're 1 billion items, it would require massive amounts of memory. And if in our memory hierarchies in today's computers, it would probably mean swapping to disk. It wouldn't mean you can't hold it in memory. You got to put it onto disk. And if you put it onto disk, even if it's a fast disk, an SSD, a solid state drive, or what have you, it's going to be tens of thousands or more times slower than memory. It's going to have a huge impact on memories, on performance, if you're swapping this out. And if you do that for every successive step, you're enormously slowing down your pipeline. So that's a anti-pattern we want to avoid. This idea that, for each step of this, we're computing a complete data structure here. Fortunately, we don't have to do that. Fortunately, non-strictness, ladies and gentlemen, comes to the rescue. Okay? So instead of doing 2 array, I return to my original instructions to stream here. And it turns out that this is one of the ways that streams are completely different than arrays and this non-strictness, because streams will allow us to defer computation until it's needed, defer creating the data structures until it's needed. But more fundamentally, they will allow us to perform the computation incrementally. So I'd like to show that, okay? Watch this. Watch this. I am going to use this as a case here. So we're going to size or length? I think it's length. So I'm going to change this slightly. There it is. Okay. So ladies and gentlemen, what am I computing here? Anyone? What am I computing? What is that? It's a construct of some significance to the author.
Word count.
Word count. It's their word count, right? Yuvan is particularly familiar with the importance of word count in some contexts. It's no exaggeration to say that in my lifetime, I've probably spent dozens of hours, maybe hundreds of hours, focused on trying to fit text within a certain word count. It's an incredibly time-consuming operation. Okay, so this is word count, ladies and gentlemen. Okay. In order to get to that point, I go with an array here. I go through, this is the final step here. I get out a filtered thing. Before that, I'm getting out a different data structure. Before that, I'm getting out a different data structure of lines. Each successive data structure involves this successive, entire collection being materialized if done not naively. Now, if I do this instead with a stream, watch what's different. Okay, watch what's different. I'll say size here. That's fine. I'll keep it with size, but I'm going to do it with the stream. Okay. Notice I get the same answer, right? But how I get it is different, and that makes all the difference. Why? Well, let's go peel back the onion one step. What do I get out of this? Anyone tell me? What do I get out of this? How many things has it computed so far? In order to get to this point, what has it computed? Yeah, it's only, yeah. But I tell you, I'm at the output of this stage. That's what this is, right? So I'm getting to the heart of the issue here. This one word, to get this output, what parts of this pipeline has it executed? Ladies and gentlemen, it executed here each and every stage of this pipeline to get to this one word. It just executed it on the first elements, right? It handled the first line of the file. It turned it into a stream. It split it into words, and it filtered this out. So has it brought all of the data structure into memory of all the contents? No. No, it is not. No, I could count that word. If I were counting the size, I could count that word. Do I need to keep it around after I count it? No, I don't need to care. I can throw it away. And I can go into the second word. I can go into the third. I can go into the fourth. Maybe then I go into the second line of the document. Each time I'm counting the number, I'm just accumulating it. That's the size. And I'm going on to the next word, and the next word, and the next line, and the next word, and the next word. At no point am I bringing the whole data structure into memory. I'm not reading the whole thing into memory as a document, billions of items of Nolian text. I'm not bringing that into memory. Ladies and gentlemen, at any point here, instead, I'm incrementally processing each word. Do you get that point? So, here I could do, I'll drop the first one, and then I'll take one and I'll force it. Okay. And now I've got the second word, right? And after that, if I were to count it in my size, I will go on and I will get the next word yet. Okay. And it's doing all the work needed to give me each successive word. Do you understand that point? It's, if needed, it's getting another line from this file and splitting it up, right? Getting a line from the original file, splitting it up. But it's not reading it. It doesn't need to read in the whole file. It doesn't need to put it all into a collection of lines that are huge. It doesn't need to split each of those collections of lines into a collection of words. Instead, it's doing it incrementally, step by step. It's executed the complete pipeline here on an incremental basis, word by word by word by word. And that, ladies and gentlemen, is memory sipping. What I mean by memory sipping is you're not just sort of sucking up tons of memory. You're using only small bits of memory at a time, as needed to do each successive element at a time, not bringing the whole into memory, always just handling each element in its successive operations of it as needed. This is huge for its implications in memory, because if we were operating off something with billions of words, bringing it into memory would be absolutely prohibitive. But we could read each little bit. We take the first line, we split it up. That's only a very small number of words in it. For each of those words, we go and we filter them, we count them, accumulate our count, go on to the next word, go on to the next word. Eventually we get to the end of the line. Okay, now it's time to go to the next line. All those words have been thrown away, Milan. We don't keep them around. We don't keep them around. So in short, streams, ladies and gentlemen, though it may not have struck you at first blush, streams are a key for incremental processing. They're the key for moving from pipelines which operate in big chunks, whole collection here, next step outputs a new collection, next step outputs a new collection, output next step, new collection, to instead processing each element of the first, one element of the first collection is mapped in the second operation, the third operation, the fourth operation, fifth operation, to a successive element to where it's consumed, say with counting, and then the next one, each successive operation, never needing to bring in more than a minimal amount into memory. And it turns out that's completely liberating. And it turns out that is what Spark does. And this is one of the reasons Spark is built atop this framework, because it allows you to engage in this incremental processing of data rather than wholesale kind of working with collections as input, collection as output. Does that make sense, what I'm saying? This kind of view of going from streams to going from arrays where we, here, well, this is still get lines, but it's to array. So we can't do this anymore. But here with an array, we'd be operating with these large data structures. Each successive operation processes a large data structure, materializes it, creates it, defines it. And we just can't do that with data science. We have to do things incrementally. And that's what laziness in streams allows us to do. Okay. Now, in our next lecture, we'll be seeing the multiple ways in which this is supported in Scala. The three ways we'll be talking about, as I mentioned, for non-strictness, are associated with call by name, associated with lazy values, associated with streams. And there's actually one more one as well, which is you can have a data structure and you can convert it to a lazy data structure, okay, which will allow it to be processed in a non-strict way, which is favorable. Anyway, that will be next time, okay? I think we're dealing with adverse air quality here. I think the machines outside are unfortunately operating too close to the intake vent. So if anyone needs to speak with me, I'd be glad to do so. But I will do so from the airy, the comfortable air in my office. Okay. Thanks very much. And hopefully some people were able to attend remotely here.